So welcome back once again, and so far we have been talking about electromagnetic induction and motional EMF, okay, where we talked about this kind of thing, you know, each and everything over here, and where this rod is moved to the left with a constant speed v, and the magnetic field, like before, is like this. Okay. Now what we have is that we consider that between the P and Q, this arm, there is a this has a resistance small r, and this makes a loop. So let us also consider that the rail, the part of the rail Q, R, R, S and SP, they have zero or negligible resistance. Okay. So the overall resistance of this loop becomes equal to small r ohms. Okay. Now, upon this we have an EMF which is BLV, or like my teacher Vishnu Bihari Lal, VBL. Okay. So the current from Ohm's law becomes equal to the EMF divided by the resistance, and we get VBL or BLV divided by R. Okay. Now let's see. What is the force on the RPQ? That force, when the current is I, then like I said, Bill sine theta, and sine theta is equal to 1. So this will become equal to I into the magnitude of L cross B, which will turn out to be equal to ILB. Okay. I substitute for the value of I from here. This is BLV upon R into L into B. So this turns out to be equal to B square L square V upon R. And this force on the RPQ is due to the drift velocity of charges responsible for the current along the rod and the use of Lorentz force on these charges. So we get this relation. This is another method. Alternately, we see that PQ is being pushed with a constant velocity. So there is a power required to do so, and that power is equal to force into velocity. Okay, you must remember that. So force into velocity, and the force, this turns out to be equal to, okay, B square L square V upon R, which is the force multiplied by V. So the force on the arm is this, and multiplied by V. So what I get is B square L square V square upon R. Okay. This is the power required to do so. This power is dissipated through the resistance R, and the power dissipation is given as the heat generated due to Joule heating. So this is equal to I squared R, and I is equal to BLV upon R. So this whole square multiplied by R. So this again turns out to be equal to B square L square V square divided by R. So these two, they equate to each other. Power is required, we provide that power, and the power is dissipated through radiation from the surface of the resistor through which the current is flowing. Okay. Now one more thing. How is delta phi related to a change in the value of charge? So look here, it's very simple. That the magnitude of EMF is equal to delta phi upon delta t. Okay. So this I can write as R into I also, because this is R is the resistance and I is the current through it, and I can be written as delta Q upon delta T. So if the two times are equal, then they cancel out, and delta phi becomes equal to R into delta Q. Okay. Or we can say that delta Q is equal to delta phi upon R. So there is a linear relationship as is evident from this set of equations. Okay. So I can draw delta phi, delta Q, and the slope is equal to R. Reverse that and the slope becomes equal to 1 upon R, etc. Now, look here. Suppose this field, okay, I'll tell you later on, but first of all we are going to talk about what are known as the eddy currents. Now, after the exercise that we have done, I am going to discuss just an exercise where I have a sector where the magnetic field is out of the board, uniform everywhere, and there is a rail of thick wire, and there is a sliding rod, as we have done before. Now this area ends up over here, and we may start from x is equal to 0 here and take this rod along to the right. So what happens? While this rod is taken away, okay, the flux is changing. In fact, it is increasing up to this point. And thereafter, if this rod is brought here, or here, or here, or here, okay, up to this point, x is equal to 2b, well, the flux is there, but it is not changing. So therefore, we will not get an EMF there. If we return back from here, back up to this point x naught, then initially up to this point x is equal to b, there will not be any change, but after that the flux will keep on decreasing. The values are given, and normally we are asked to plot the flux as a function of x, the EMF that is developed as a function of x, the force that is there as a function of x, and the power as a function of x. I will not indulge myself in that exercise. It's easy, and you must do it all by yourself. Okay. The next item I want to discuss in this continuation is a very interesting subject of localized currents, which are called eddies, are Foucault currents. Actually, the name is written as Foucault, but it is read as Foucault. So, Foucault currents. That's very interesting. Suppose there are magnetic lines of field going from left to right, okay, and there is an area over here, and this is a ball or a plate which is going inside or outside. Okay. So when they cross, when they are inside, immersed in the magnetic field, the flux is unchanged. But no sooner than they get out of it, there is either a flux increase or a flux decrease. In that case, locally some currents will flow. These currents, because of the induced electromagnetic EMF, because of the EMF, locally there will be currents which will be possible. And what happens? The motion of the plate or ball, it damps. Why? Because the energy that they have got is partially used to, in the form of the eddies, and the eddies, when they flow, then there is a Joule heating, and which are the Joule heating allows the energy to dissipate over there. Compare that to a case of a pendulum in Earth's gravitational field. You can see the pendulum goes from left to right and back to right and back to, like that, to and fro kind of a motion is there. And the time period is 2 pi L over G. Now when this damping takes place, then the motion stops after a very small length of time, okay, a small amount of time. Such things, the eddies which happen, they have many applications. I'm just enumerating the applications, like magnetic braking of trains. Okay. They are utilized, the eddies can be utilized in magnetic braking of trains. So, brakes. Number 2, they can be used for electromagnetic damping in certain galvanometers, particularly the throw type of galvanometers which keep on moving and we want that to stop. So some kind of a tapping arrangement is there by which the damping is introduced and the galvanometer deflection is brought to a stop. And of course, when there is a current, then there is an I square R heating. So because of this change in the magnetic flux, we introduce eddy currents which heat up the environment there, and that is how induction furnaces they function. And the fourth application which is here is electric power consumption meters. Okay, they have their own physics, and I'm not going to indulge into the details here. And the next item that we are going to talk about is the inductance. Okay, and inductance is of two types: the mutual inductance and the self-inductance, and we'll talk about the details to come prepared for the next lecture where we discuss inductance. Okay, thank you.